So I'm Dr. Shankaraiah from Department of Physics. So in the last presentations, I have discussed about modules on applied physics. So today I'm going to discuss about crystal structures. Which is a module 1 in applied physics. So in the first topic in crystal structures is introduction. Okay, so I'm going to give introduction to crystal structure in this today's presentation. So the study of crystal structures or geometry helps us to understand diverse behavior of solids in their mechanical, metallurgical, electrical, magnetic and optical properties. So the first question when we start this topic is that what is the importance of crystal structure, or why do we need to study crystal structures? Do they have any importance that can be used in applications? So the first thing we are mentioning is that the study of crystal structure helps us to understand behavior of solids in their mechanical, metallurgical, electrical, magnetic and optical properties. If you know the crystal structure of the solids, you can understand the different properties of solids. Okay, so basically solids are different types. We will discuss in detail. Okay, so understanding these crystal structures will help us understand the properties of these solids, different properties: mechanical, metallurgical, electrical, magnetic and optical properties. Okay, so this number 2 is a reference book where from which I am taking the material. So one of the example I want to discuss about the crystal structure, where we use the crystal, or what is the importance of the crystal structures. So one of the example is shape memory materials. These shape memory materials they remember their shape. That is why they call as shape memory materials. For example, if I take material, for simplicity, I am considering a two-dimensional material, two-dimensional square unit cell. So I have a solid with all the unit cell with square unit cells. Okay, so we will see what is the unit cell. Unit cell is the smallest geometrical unit. Okay, so by repeating which we will get the complete solid structure. Okay, so you have this square unit cell in 2 dimensions. So let me say this is square unit cell. So I have a material solid with all this unit cell is a square. Now if I cool this square, if I cool the material, so this is a solid, it's a material in the solid phase, and this solid is having all square unit cells. Okay, so if you look at the solid under microscope, you will see, for example, I am taking this as example. In general, we need to discuss a 3-dimensional structure, but I am taking 2-dimensional for the simplicity, for the convenience to understand it easily. Okay, so I have a square unit cell. This solid has all square unit cell. Now I am going to cool this material. So then this square unit cell can deform to rectangle unit cells. All the square unit cells are going to deform into rectangle unit cells when I cool it. Okay, now so I have one kind of phase. This is called austenite phase. You don't need to remember all this. And this is called martensite phase, right? So I have a solid material which has square unit cells, right? So this crystal is going to have all square unit cells, for example. And when I cool it, these square unit cells are deforming to rectangular unit cell, right? So this is a crystal structure. Rectangular unit cell is another crystal structure. Now there is a phase transition from square unit cell to rectangular. Now I am going to heat it back. I am going to heat this solid way in which there are rectangular unit cells. When I heat this material, these rectangular unit cells are again going to deform to solid with all square unit cells. So basically, there are materials which are called shape memory materials, and they will change their crystal structure from one crystal structure to another crystal structure. When you cool it, when you heat it, they will remember their original shape and they will come back to their original shape. Okay, so these are called shape memory materials. To understand these shape memory materials, you need to understand the crystal structures. That is why I am telling you this. This is an example of what is the importance or what is the application of crystal structure, where we can use the knowledge of this crystal structure in real life. So these shape memory materials have many applications, ranging from dentistry to dentistry. Even they use in aeroplanes, right? So blades, as a blade. Okay, so using understanding crystal structure, you can use the knowledge in understanding different materials. These are also called smart materials, right? So they have many applications in technology and industrial applications. Okay, right? So this we can do. These materials can undergo these shape changes, crystal structure change on cooling or heating, or by applying stress. Also, these materials will go from one crystal structure to another crystal structure. So knowledge of this crystal structure will be very helpful to understand these materials, to tune their materials to various applications. So a solid. So now we are going into to understand introduction of this crystal structure. Once we know the applications or what is the use of these crystal structures, right? So a solid consists of atoms or clusters of atom arranged in close proximity. So solid is, we know that there are three different phases of materials. For example, actually there are four materials, but in general we'll discuss only three materials, three different phases, right? So the three different phases of the materials. So three phases of materials phases. One is solid, and another one is liquid, and another one is gas. So three classes: solid, liquid, gas. And we classified this solid is going to have all the atoms arranged very close by. Solid is the one solid. In solid, if you look at the atomic arrangement, all the atoms are whatever the atoms. Suppose if it is a gold material, all the gold atoms are sitting very close to each other. Okay, all the atoms are sitting on each other. We will discuss where they are sitting and in detail in the coming slides. Okay. So in solids, atoms are arranged in close proximity. They are arranged in very close to each other. We know that liquid, there is a moderate distance between the atoms. Okay, liquid, there is a moderate distance between the atoms. Whereas they need not be a regular arrangement. Whereas in gas, there is very large difference between the distance between any of the two atoms, right? So solid consists of atoms or clusters of atoms arranged in close proximity. So the diverse behavior of solids in the mechanical, metallurgical, electrical, magnetic, and optical properties are closely related to the scheme of arrangement of atoms within a solid. So different behaviors of these solids, the changing behavior of the solids in mechanical, metallurgical, electrical, magnetic, or optical properties are closely related to the arrangement of these atoms. How did they arrange? For example, if you take a particular material, how the atoms are arranged in that material. Okay, based on the arrangement of atoms, the properties can change. Mechanical properties can change, metallurgical properties can change, electrical properties can change, magnetic and optical properties can change. So the important point is that based on the arrangement of the atoms within the solid, the properties of the material solids can vary. Okay. In amorphous solids, the arrangement of atoms is random, while in crystals, there is regular arrangement of atoms. Now, simply, in a vague way, we have classified these solids into two materials. For example, now you have, okay, solids, we will discuss in detail, but let us say solids are classified into two categories. The first one is crystals, and the second one is amorphous materials, amorphous. Okay. Solids are classified into two categories based on the atomic arrangement. Based on the atomic arrangement of these materials, solids are classified into two categories: crystals and amorphous. So crystal, we are saying that crystals are going to have regular arrangement of atoms. Okay. So there is a regular arrangement of atoms in crystals. Okay. All the atoms are arranged in a regular manner. Okay. Whereas in amorphous solid, atomic arrangement of atoms is random. Okay. So in amorphous also, you can have local order, but you are not going to have a global order. So arrangement is not very regular. So it is atomic arrangement is random. Okay. Random atomic arrangement. Okay. So solids which are having random atomic arrangement is called amorphous solid. And the solids which have regular atomic arrangements, they are called as crystals. So basically, based on the atomic arrangement of atoms, you can classify solids into crystals and amorphous materials. Crystals where atoms are arranged in a regular periodic manner, and amorphous materials there is no regular periodic arrangement of atoms. Atoms are arranged in a random way. Okay, and how do we understand these atomic arrangement, regular atomic arrangement or random atomic arrangement? This can be understood using X-ray diffraction. Using these experimental techniques called X-ray diffraction, you can understand whether it has crystal structure, whether it has regular periodic arrangement of atoms, or whether it has random arrangement of atoms. Okay, and this X-ray diffraction was first invented by Max von Laue. Okay, so he is the first scientist who invented this X-ray diffraction that is now widely used to understand these crystal structures, and in many different areas of material science and physics. Chemistry also, they use biology, in all the branches of science now X-ray diffraction is used widely to understand different properties. Crystal structure first to start with, and atomic arrangement of atoms. Okay. So solids are classified into the three categories basing on the atomic arrangement of arrangement within the solids. Okay, so we have said that there are only two types of solids. Solids are classified into two categories. So solids are classified into two categories. We said one is crystals and other one is amorphous materials. So basically crystals are again classified into two categories. One is polycrystals and other one is single crystals. Okay, so overall solids are classified into three categories based on the atomic arrangement: amorphous material and polycrystals and single crystals. Single crystals and polycrystal both are crystals, and amorphous material is not a crystalline material. Okay, so you can clearly see the atomic arrangement in these three different types of solids. Okay, this is the first one is crystalline structure. See, all the atoms are arranged in a regular and periodic manner. Everywhere all the atoms are arranged in both direction. You can see all the atoms are arranged in a regular periodic manner. If I can draw in three dimensions, even in third dimension also, x, y. So if it is x and if it is this one is along x, y. If I have third direction also, if you look at the atomic arrangement, even in the other z direction also, you will see there is a regular periodic arrangement of atoms because this is a single crystal. Now this is polycrystalline material. Polycrystalline material. So in single crystal you have a global order, long range order. We will discuss about all this long range and short range. So in single crystal you have a long range order, whereas in polycrystals you have a local order. See, so polycrystal, single crystal, there is only one crystal. Polycrystal means there are small crystallites. So this is one crystallite, for example. This is one crystallite. So in this small crystallite there is atomic arrangement of atoms in this direction and again in the other direction also. Right? So in both direction there is atomic arrangement of atom, regular atomic arrangement of atoms, but this is only in small area. In small area you have this regular arrangement of atoms. Again there is another crystallite. Again there is another crystallite in which the atoms are arranged in a regular periodic manner, but their orientation is different. Okay, so there is anisotropy. The anisotropy is different in polycrystalline. Okay, so polycrystalline means you have many small crystallite. Poly means many. Okay, many small crystallite. In every crystallite you have regular periodic arrangement of atoms. That is why we call it as polycrystalline material. This is a single crystalline material. You have a regular periodic arrangement of atom over all the material, which is called single crystal. Okay, polycrystalline means there are many crystallite, small crystallite in which there is atomic arrangement of regular periodic arrangement of atoms, but this is only in a small crystallite. There are many such crystallites, so that's why we calling it as polycrystalline material. And coming to the third one, which is called as amorphous solid, we know that in amorphous solid there is no regular arrangement of atoms. All the atoms are sitting in random manner. Okay, so there is no regular arrangement of atoms. So here you have regular arrangement of atom, which is long range order. Here you have short range order. Only for smaller distances you have regular arrangement order, whereas in amorphous material, random, there is no order, random atomic arrangement. Okay, so yeah, so there are three different types of solids based on the atomic arrangement of the atoms in that solid material. and the three solids are single crystals, polycrystals, and amorphous solids. Single crystals and polycrystals are coming under crystals, but in single crystal you have long range order. Over long distances you have regular periodic arrangement of atoms. In polycrystals you have many different crystallites. In each crystalline there is regular periodic arrangement of atom, but that is only for shorter distances. That is why we call it as short range order. Whereas in amorphous solids the atoms are arranged in a random manner. Okay. So let us see in detail what are these three different types of solids. Single crystals. X-ray diffraction studies have shown that the atoms in a crystalline solids are arranged in a regular periodic pattern in 3 dimensions. Okay. Yeah. So this is a figure A that we have seen. In single crystal, if you look at if you use the X-ray diffraction technique, experimental technique, and look at this experimental result of the single crystal, you will find all the atoms are arranged in a regular periodic manner in 3 dimensions, not only in 2 dimensions but in 3 dimensions, right? The arrangement of atom in specific relation to each other is called order. So we are defining now a term called order. What do you mean by order? How do you define a order? The arrangement of atoms in specific relation to each other. I have an atom here, another atom here, another atom here. So you can define a relation between these 2 atoms. The first atom is at a distance x, and the second atom is at a distance of x plus a. Third atom is at a distance of x plus 2a. Similarly, along this direction also you can decide if it is x along y, this is at y plus a, y plus 2a, y plus 3a, like that. So the relation, the arrangement of atoms in specific relation to each other. By looking at the relation, you can locate the atoms' atomic positions. Okay, so then we can define the order. So order is nothing but the arrangement of atoms in specific relation to each other. That is called order. Okay. So if you cannot define the relation, then there is no order. You cannot suppose here there is a clear order. So you can define x plus a, x plus 2a, and x plus na. At every atom you can find out the atomic position using a particular relation of x plus na. First atom is x plus x, second atom is x plus a, third atom is x plus na, x prime is equal. Fourth atom is x plus 3a, like that. If you do not have this regular atomic arrangement, you cannot define this kind of order. So order is nothing but the relation between you. If you can define a specific relation between 2 atoms, then you can define order. Okay. In crystal, the order exists in immediate neighborhood of a given atom as well as over long distances corresponding to several layers of atom. Therefore, crystals possesses both short range order and long range order. Okay. So we are saying here crystals. Okay. In crystals, you can define short range order and long range order. Long range order means this relation, this specific relation between atom you can define over long distances to the size of the material. Okay. Short range order means you can define this relation only for smaller distances. Okay. Then the material is going to have short range order. Long range order, the relation that the order you can define or the arrangement of atom is for large distances. Okay. Short range order means the arrangement of atom is there, order is there only for shorter distances. Okay. So crystals are going to have both short range order and long range order. So we have defined order and we have defined what is long range order and what is short range order. Okay. So in single crystal, since the periodic arrangement of atoms differs in 3 directions, the physical properties vary with directions and therefore they are called anisotropic substances. So in single crystals are also called as anisotropic substances because they are oriented in a particular direction, right? So anisotropy means nothing but the directional dependence, how the atoms are oriented in a arranged in a particular direction. So that then we call it as anisotropic. If there is no directional dependence, we call it as isotropic. Isotropic means no directional dependence. They are oriented in random way. If there is directional dependence, atoms are oriented in a particular direction in a regular periodic manner. So there is a directional dependence. If there is a directional dependence, then we are going to call this material, there is anisotropy. There is anisotropy present in these materials, and here single crystals are going to have this anisotropy present in these materials because they have a clear arrangement of atoms in a particular direction. So that is why single crystals are called as anisotropic substances. And the examples of single crystals, quartz, diamond, rock salt, that occur as large size single crystals. So quartz, diamond and rock salt are the examples of single crystals. Okay, so single crystals are also called as anisotropic substances because anisotropy means directional dependence of arrangement of atoms. In single crystal, there is clear directional dependence of arrangement of atoms. That is why single crystals are called as anisotropic materials, and quartz, diamond and rock salt are examples of single crystals. So the next one is polycrystalline solids, polycrystalline materials. Polycrystalline solids consist of fine grains. Okay, so you have different kinds of grains, so there are many grains, fine grains having size of 10 power 3 to 10 power 4 angstrom. 1 angstrom is, we know that 10 power minus 8 centimeters and 10 power minus 10 meters. So it's very small, 1 angstrom. So 10 power 3 into 10 power minus 10, it will be very small. Okay, so each grain is 10 power 3 to 10 power 4 angstroms, right? Separated by well-defined boundaries. So there is a boundary between each of these grains. Polycrystalline materials consist of fine grains, and each grain can be around 10 power 3 to 10 power 4 angstrom size, and all these grains are separated by well-defined boundaries. There is a boundary between these grains. These boundaries, these are also called as so boundaries, well-defined boundaries, but oriented in different direction. How are we going to define the boundary between these grains? Because in each grain the atoms are arranged in a particular direction. Okay, that is why we are able to define the boundary between these fine grains. All these grains atoms are not oriented in one particular direction. In each grain the atoms are oriented in particular direction. So when you look at the all the grains, in each grain there is a particular way of arrangement of these atoms. So that is how we define these boundaries, grain boundaries, right? So each such grain is in a single crystal of an irregular shape. Since the grains are oriented randomly, a polycrystalline material is isotropic and the physical properties do not vary with the direction. In single crystal, we know that there is isotropy. There is anisotropy presented in single crystal. So that is why single crystals are called as anisotropic substances. Whereas coming to the polycrystalline materials, each grain is oriented in a different direction. So overall, there is a random orientation and in polycrystalline materials, and that is why these are called as isotropic substances, and the physical properties do not vary with the direction because there is no directional dependence. There is a random orientation of these grains. Majority of the natural solids have polycrystalline structures. Metals are examples of polycrystalline solids. Okay. Polycrystalline material consists of very fine grains. There are many fine grains in polycrystalline materials, and each grain size is around 10 power 3 to 10 power 4 angstroms. It's very important. Angstrom. If there is no angstrom, it's very big number. So 10 power 3 to 10 power 4 angstroms. And each of these grains is separated by a boundary called grain boundary. And in each grain, there is a arrangement of atom. In overall, if you look at, they are oriented in a random way, and each grain is oriented in a random direction, and hence these polycrystalline materials are called anisotropic substances, and these physical properties do not vary with direction. Okay. And the examples of polycrystalline materials is metals. Metals are all examples of polycrystalline solids. Okay. So, before discussing about the third type of this solid, there are different types of crystals that are classified based on the electrostatic forces between the two atoms. Right? Crystalline materials have regular arrangement of atoms, and there are atoms, right? Regular arrangement of atoms. What is the kind of force that exists between the two atoms, nearby atoms, right? So the atoms are bound to each other by electrostatic forces. Depending on the nature of the bond between the neighboring atoms, crystals are classified into three categories. Okay, what kind of forces that exist in between these two atoms? Based on these nature of these bonds, nature of the bond between these neighboring atoms, crystals are classified into three categories. You can have metallic crystals, covalent crystals, and ionic crystals. Okay, so this classification is based on the bond between the neighboring atoms. what kind of bond there exists between the two atoms, neighboring atoms. So based on the bond between the two atoms, crystals are classified into three categories: metallic crystals, covalent crystals, and ionic crystals. So what are these ionic crystals? Ionic crystal, the electron is transferred from one atom to the another atom. So the atom which lost an electron is called anion. The atom which gained an electron is called cation. Okay, and the atoms exist in the crystal as ions, and hence the name ionic crystal. The interatomic forces in such crystals are non-directional. Okay, what do you mean by ionic crystals? Ionic crystals are the material in which atoms are going to lose. Some of the atoms are going to lose electrons, and some of the atoms are going to gain electrons. So there are ions present in material, and those ions are called cation and anion. Such a crystal is called ionic crystal, and in this ionic crystal the atomic forces are non-directional. Okay, coming to the second one, covalent crystals. In covalent crystal the atomic forces are directional, where the electron is shared by the neighboring atom. In covalent crystals, electron is shared by the neighboring atom. So if there is one electron that is shared by this atom and this atom, so they are going to share the electrons. So okay, sharing of the electron present between the two atoms, such kind of crystals are called covalent crystals, and the interatomic forces are directional in covalent crystals. Coming to the third one, metallic crystals, where the electrons are very loosely bound to the corresponding nuclei. In metallic crystals, there is neither the electron is loosely bound to the corresponding nuclei. Okay. So these type of crystals are called metallic crystals. Okay. So based on the bond between the neighboring atoms, there are three different types of crystals: ionic crystals, covalent crystals, and metallic crystal. Ionic crystals, there is a losing or gaining of electrons, and there are ions present in the crystal, so that is why these are ionic crystals. Covalent crystal, there is a sharing of electron between the atoms, so that these are covalent crystals. And metallic crystals are the ones where there is a loose bounding, the electron is going to bound to the nucleus very loosely, so these are called metallic crystals. Okay. So we have discussed about single crystal and polycrystal. The third one is amorphous solids. Solids, materials possessing only short range order, are called known as amorphous solid. These materials maintain a fixed volume and shape and resemble solids in their external features, but internally they do not have the ordered crystalline arrangement. So amorphous materials, even though they are looking like crystals, when you touch them, you feel that these are crystals. When outside, when you look at, we feel that there is a ordered crystalline arrangement, but internally there is no ordered crystalline arrangement in amorphous solids. Okay, so amorphous solids are going to have very short range order, so that the order is only for very small distances. And these materials maintain fixed volume and shape and resemble like solids in their external features, but in general they do not have any atomic arrangement internally, so there is no crystalline arrangement. The atomic arrangement is random in these materials. They are in fact considered as supercooled liquids having a very high viscosity. So amorphous solids are the materials which do not have long range order. They can have short range order present in them. Short range order means only for very small distances the atoms are arranged regularly. But if you look at the overall, there is no order. Okay, so that is why amorphous solids are going to have short range order. And these materials, when you touch them, you feel like they are solids, but they do not possess any internal crystalline arrangement. Okay, and the examples of these amorphous solids are glass, rubber, and many polymers are examples of these amorphous solids. Okay, so glass and rubber and amorphous solids are the examples of these amorphous solid, and they are having high viscosity. Okay, so a given atomic arrangement in a material is called a phase. Okay, so we know that there are three phases: liquid, gas, and solid. So the given atomic arrangement, based on the atomic arrangement only, we have classified them as three different phases. So phase is nothing but the atomic arrangement in a material. Okay, so if the atomic arrangement in the crystal changes, we say that there is a new crystal has formed, and hence phase change occurred. You have one kind of atomic arrangement initially. Now suppose we have applied pressure on this material, then the atomic arrangement changed. That means there is a change in phase. Okay, so when there is a change in phase, there is a new crystal that is formed because we have applied external force. Okay. Thus, a given chemical like water may exist in different phases, for example, vapor, water, and ice phases. Phase is nothing but atomic arrangement, a particular atomic arrangement. Okay. Since the atomic arrangement everywhere in the crystal is same, the crystal growth occurs at a fixed temperature. Okay. So you can grow the crystals at a fixed temperature. The atoms in the crystal are arranged and dispersed like soldiers in the army, and each soldier going through a particular movement. Okay. So we have defined what is a phase, and how phase is nothing but the particular arrangement of atoms, and when if you apply any external force, there is a change in the atomic arrangement, so there is a new phase. So there will be phase change when you apply external force, right? For example, how do you grow this crystal? You can grow this crystal at a particular temperature. So periodicity, I have been saying that the atoms are arranged in a regular periodic arrangement. So how do you define the periodicity of a particular atomic arrangement? You can define the periodicity of a particular atomic arrangement in a material by using AX, R is equal to AX plus BY plus CZ, where XYZ are unit vectors in XYZ directions. Note that periodicity is the only condition for crystallinity. To define the crystallinity, you can use the periodicity. Okay, using this R is equal to Ax plus By plus Cz along XYZ are the units vectors along XYZ directions. So using this periodicity, you can define the you can define the crystallinity of a particular material. So these are the references in which I have used and to prepare this material. So to summarize, I've discussed about classification of solids into single crystal, polycrystals, and amorphous materials. And then I have also defined what is order, and I have also defined what is a phase. I have defined, I have also classified crystals based on the bond between the neighboring atoms, and I've also defined what is a periodicity. Okay. So in the next presentation, we will discuss some more topics in crystalline structure. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.